There were originally 45 problems in this review assignment, but then I recently realized that there were a couple of problems that were left out that should have been in there. So these are back, just two more problems. These are both limit problems. Of course, there's two kinds of limit problems. Let me briefly explain. There's limit problems where, say, x is approaching a number. And we did some examples like this earlier, so I won't even go into how to do this. But then there are limit problems where x is not approaching a number, but x is approaching either infinity or negative infinity. And once again, I went through all this in the lecture and explained this is oftentimes what we call end behavior. And the way you solve these two kinds of limit problems are totally different. So earlier in this review, we did some limit problems where x is approaching a number. However, there were not any problems where x approaches either infinity or negative infinity. So that's what these two are. And because these two kinds of limit problems are totally different, I want to actually go ahead and do a couple of these. Now, there's some different ways that people like to solve these, but what I like to do is I like to use the method where you look at the top and the bottom and you do what's called reduce to the leading term. In other words, the leading term is the term with the largest exponent. So in this numerator, there's three terms. 25x cubed would be called the leading term. So normally what you do, you just ignore the remaining terms. And then you go to the bottom. There are four terms in the bottom, but the 30x cubed is the leading term. So it's almost like you cancel or ignore these. So then what you're left with is 25x cubed over 30x cubed. And at this point, we can go ahead, if possible, cancel and reduce. In other words, look at x cubed over x cubed. Those cancel out. As a matter of fact, 25 over 30, if I divide both the top and the bottom by 5, I get 5/6. So after do all this stuff, it turns out for this problem, you actually don't even have any variables left in your expression, which means when you don't have any variables left in the expression, the answer is just the number. So the limit as x approaches infinity of all this is just 5/6. And the key to that is, as you do these a lot, sometimes you recognize right away when the leading terms have the same exponent in the top and the bottom. It's like everything cancels out and your final answer is just the ratio of these coefficients. So really the answer to this problem is 25 over 30. Of course, since it's a fraction, we reduced it to 5/6. So the answer is just 5/6. Here's another one. We use the same method. The limit as x approaches infinity of x squared plus 17 over x cubed plus 9. In this case, the leading term on the top is x squared, so the 17 I ignore or cross out. In the bottom, the leading term is x cubed, so I eliminate the 9. So I'm left with the limit as x approaches infinity of x squared over x cubed So once again, I should go and cancel out what I can. So I can cancel out x squared in the top and the bottom. And I'm left with the limit as x approaches infinity of 1 over x. And now a little common sense says, well, x approaching infinity, to see what happens here, let's imagine I put in a huge number for x. I mean, you could put in infinity, but if you want to visualize it, what if I would put in 1,000,000 for x? What is 1 over 1,000,000? It's a very, very, very small number. Or 1 over 1,000,000,000,000. Or 1 over the biggest number you can imagine. Well, as this denominator, as this number gets huge, you know what this thing gets really, really close to, or what it approximately equals? 0. If this denominator gets so large, this fraction is more or less 0. It never actually reaches 0, but it is so small, we can basically say the limit of this equals 0. All right, so those were the 2 extra bonus problems that were not in the original review, but wanted to make sure you had a couple of these also to practice.